Welcome to this explainer. We're getting into the literal nuts and bolts, or rather the pipes and cement, of flawless plumbing systems. We'll trace the journey from the absolute micro level, like the exact chemistry of a single PVC joint, all the way out to the macro level, specifically looking at how trapped air moves through miles of municipal pipeline. Because, as you probably know, in fluid dynamics, the tiny details completely dictate the large-scale efficiency. Okay, let's just jump right in with a question that impacts practically everyone's wallet, whether you manage a massive commercial facility or just own a home. Are you actually being billed for air spinning through your water meter? Now, I know that sounds totally absurd, right? But the physics of water delivery means this is actually a very real, very common problem. Check this out. Trapped air can actually inflate commercial water bills by up to 30%. That is a huge financial drain, and it's completely invisible to the naked eye. It really sets the stakes for why nailing your system construction and pressure management is just absolutely crucial. So here is our roadmap for today's explainer. First up, the flawless plumbing system. Second, the perfect PVC joint. Third, the chemistry of solvent welding. Fourth, friction and pipe elbows. And finally, number 5, eliminating trapped air. Let's get into it. Section 1, the flawless plumbing system, building from the micro to the macro. Section 2, the perfect PVC joint, the foundation of flow. To really get this, think of a plumbing system like a massive interconnected highway. Every single fitting alters the journey. When we look at this foundation of flow, the data highlights something really critical. The bottom 20% of the fitting socket is actually the strongest part of the entire joint. So if your pipe is cut even a little crooked, it's not going to bottom out correctly inside that fitting. You're literally losing structural integrity before a single drop of water even enters the pipe. So, to get that perfect, fully seated fit, professionals swear by these 5 non-negotiable steps. Clean the material, cut squarely, deburr and bevel, apply primer, and then apply your cement. Step 3, the deburring process, is something we really need to highlight. Those tiny little shards of plastic left over from cutting, if you don't remove them, they get embedded in your glue, they snag passing debris, and they create nasty microturbulence. You absolutely have to deburr your pipe ends to ensure the water flows with zero restriction. And this visual does a great job showing the difference in the tools you might use for that exact deburring process. If you go with an abrasive cloth, it gently rounds off that sharp edge, which is great because it stops the pipe from just bulldozing all your glue straight out the back when you push it into the fitting. On the flip side, if you use a file, it takes off a lot more plastic, giving you this very pronounced smooth bevel. Both ways are totally valid, but the point is, they both remove those rough burrs and perfectly prep the pipe for a flawless, turbulence-free slide into the connection. Moving on to Section 3, chemistry of solvent welding. Fusing plastic, not gluing. You know, a really common misconception is that we're just gluing these pipes together. Actually, scratch that. We aren't gluing anything. We are solvent welding. The chemicals physically melt the plastic, completely fusing the pipe and the fitting into one solid piece. The mechanics are precise. First, coat the pipe and fitting with primer to soften the PVC. Then, lay on a generous, even coat of cement. Now, when you insert the pipe, you have to give it a quarter turn. That twisting motion spreads the cement perfectly and fills in any microscopic gaps. Finally, and this is key, hold it firmly for exactly 30 seconds. If you don't, the pipe will actually hydraulically push itself right back out before the chemicals can bite. Now for the curing time, because patience really is your best friend here. While the joint might feel like it's reached handling strength in just about 5 minutes, you absolutely have to let it cure for a full 30 minutes. Giving it that proper 30-minute cure means your joint can now withstand a massive 160 psi. If you rush this and turn on the full water pressure before that cure time is up, well, there's a very good chance you'll blow apart that beautiful chemical welds you just made and create a very unwanted indoor guzzard. Section 4, friction and pipe elbows, the highway analogy. All right, so our individual joints are perfectly welded and fully cured. Now let's zoom out a bit and see how piping geometry itself disrupts the flow. Think of water zooming through a straight pipe like a car cruising down an open highway. But every time that water hits a 90-degree elbow, it's like forcing that car to make a sudden, sharp swerve at highway speeds. The water violently tumbles, it swirls, it forms these chaotic eddies. All of that turbulence generates severe friction loss, which physically drops the pressure right across your entire system, meaning your pumps now have to work significantly harder just to move the exact same volume of water. The math that engineers use to measure this is called equivalent length, and it is pretty wild to see. Look at this. Installing just one sharp 4-inch 90-degree elbow adds the friction equivalent of up to 15 feet of straight pipe to your system. Imagine if your layout has 10 of those sharp turns. You've just added the invisible friction equivalent of a massively long straight pipe. This is exactly why system designers will always opt for long radius or sweep elbows whenever they have the space for it. And that brings us to Section 5. Eliminating trapped air. Pneumatic pressure management. So, zooming out to the true macro level. All of that friction and turbulence we just talked about, combined with things like municipal line repairs or intermittent supply, creates our absolute biggest hidden enemy, entrapped air. When system pressure drops, dissolved air expands into these large compressed pockets, and this is exactly where it hits your wallet. Over 99% of water meters out there are volumetric. They measure volume, pure and simple. They literally cannot tell the difference between water and air. So when a cubic foot of compressed air pushes through, it spins the meter's dial exactly the same as a cubic foot of water would. You are, quite literally, paying for the wind. To fight back against this, engineering standards from the AWAA strictly mandate the use of air release valves, or ARVs. You can't just put these anywhere. They need to be strategically placed at topographical summits where air naturally gathers, every 1,500 to 2,500 feet on long, flat horizontal runs. And, most importantly for your bill, directly upstream of water meters so they can bleed out that air before the turbine even spins. The mechanics inside these air release valves are absolutely brilliant. They rely on a simple internal float mechanism. When a slug of trapped air enters the valve, the float drops down, which opens a vent that completely exhausts all that air right out into the atmosphere. But the very fraction of a second that actual water reaches the valve, the float shoots up, sealing it completely tight so you don't lose a single drop of water. By venting the air out, ARVs stabilize your system's pressure, they prevent really damaging water hammer, and they guarantee that you are only ever paying for the actual water you use. So, from taking the extra few minutes to properly deburr a single PVC joint, to calculating the equivalent friction of a 90-degree elbow, all the way up to placing an ARV on a miles-long municipal pipeline, every single micro detail matters in fluid dynamics. The whole system is completely interconnected. So, whether you are managing a massive facility or just doing some repairs at home, I'll leave you with this to think about. Where is your plumbing system paying for invisible air right now?